In this lesson, we'll talk about linearizations and differentials. Let's start by focusing on linearizations. A linearization is a function which I'll denote L of x, L for linearization, and it is a linear approximation to some given function. Before applying it to a couple of examples, let's get a formula for a linearization. This will amount to finding the equation of a tangent line, which is something we've done before. And for this reason, I'm going to use the following equation of a line. Y minus y1 is equal to m times x minus x1. You could, of course, use y equals mx plus b. That's fine. But I like to I'll write it as y is equal to m times x minus x of 1 plus y1. Essentially adding the y1 to the other side of the equation. So this thing here. All right, here we have a graph of y is equal to f of x. I'd like to find a general formula for the equation of the tangent line at x is equal to a. So for all these problems, you'll be given some function f of x along with a number a. And I'll put a, let's say right here. What we want to do is find the equation of the tangent line at x is equal to a, which I'll draw like this. And to find the equation of this line, we'll be using this. You need to know two things. You need to know what's the slope equal to, and what is a point that falls on the equation. And once you know both of those things, you can put them into this formula, and that will be our linearization. Well, let's start with x1, y1. We're given x1 is equal to a, so we know that. And what is y1? That is the value of the function at a, which I'll call f of a. So that's right here. So the point is very easy to find. You'll be given a, you can find f of a by using the given function. To find the slope of the tangent line, you'll take the derivative of this function and evaluate it at a, and so we get f prime of a. So in place of the slope, I'll put this. In place of x1, I'll put a. In place of y1, I'll put f of a. And I'm going to call this thing, I won't call it y, but I'll call it L of x for linearization. So L of x is equal to f prime of a times x minus a plus f of a. You could memorize this formula if you'd like to. However, all we're really doing is finding the equation of a tangent line at a given point. So what's the reason for this new terminology? The reason for it is your linearization and the actual function itself are approximately equal to each other if x is near a. So that means if you're relatively close to a, the difference between the actual function and the linearization is very small. In fact, if you want to estimate your function, you could instead put it into this formula. And this formula is a line and therefore much easier to compute. This might be very difficult to compute. This only works if you're near a, because the second you get far away from a, here's your linearization, and here's the function, and they're not really close to each other. They're not approximately equal. But as long as you're really close to a, the function and the linearization are very close to each other, so they are approximately equal. Let's try this out in a couple of examples. In example 1, I want to find the linearization, L of x, for the function f of x is equal to x cubed minus x squared plus 1 at a is equal to 2. But then we'll use this to approximate the function at 2.1, and 2.1 is pretty close to 2. Okay, so to find L of x, we know a, we need to find f of a. So let's see, since a is equal to 2, f of 2, which is f of a, is 2 cubed minus 2 squared plus 1, which is 8 minus 4 plus 1, and that is 5. So we have a point. We have the point 2 for a and 5 for f of a. We also need to know, well, what is the slope at 2? For this, we need to know, well, what's f prime of x? That is 3x squared minus 2x. So f prime of a, which is f prime of 2, is 3 times 2 squared minus 2 times 2. So that's 3 times 4, which is 12, minus 4, and this is 8. All right, great. I have the slope. I have my point. I'm going to take this information and put it into L of x. So L of x is equal to 8 times x minus 2 plus 5. And we could simplify this. You could also write this as 8x minus 16 plus 5, which is minus 9. So great, we have our linearization. I now want to use this to approximate the value of this function at 2.1. So that is, if you want to know f of 2.1, because 2.1 is pretty close to 2, f of 2.1 is approximately equal to the linearization at 2.1. And we have a pretty simple formula that's easy to put the number 2.1 into. You could either put it here or here, depending on which formula you'd like to use. I'm going to use this one here only because 2.1 minus 2 simplifies quickly to 0.1. So that's 8 times 2.1 minus 2 plus 5. That's equal to 8 times 0.1 plus 5. That's 0.8 plus 5, and that is 5.8. So what is f of 2.1 approximately equal to? 5.8. Now, you could have easily just put 2.1 into this formula and computed something close to 5.8. However, the point is, in the linearization, it'll be pretty close to this, and it's much easier to compute something that is in a line as opposed to this function, which is a cubic equation. And one final thought, wait a second, minus 9? 8 times negative 2 is negative 16 plus 5. Whoops. That should actually be minus 11. So I'm just going to go ahead and change that. And that is it for this problem. In example 2, we're going to find a linear approximation L of x, so basically a linearization, for the function f of x is equal to the square root of 1 minus x at a is equal to 0. We will then use this to approximate the square root of 0.99. This example is pretty similar to the previous one, but this last part I think is going to look just a little bit different. So to start with, we're given that a is equal to 0. And because of this, f of a, which is f of 0, is equal to the square root of 1 minus 0, which is the square root of 1, which is 1. So we have the point a, f of a, which is equal to 0 for a and 1 for f of a. So that is this and this. I now need to know, well, what is the derivative at a equals 0? Our function f is the square root of 1 minus x, which is 1 minus x to the 1/2 power. So the derivative is 1/2 times 1 minus x to the negative 1/2 times negative 1 by the chain rule. And you can write this as negative 1 over 2, the square root of 1 minus x. What is f prime of 0? If I put a 0 here, it's the square root of 1. So we get negative 1 over 2 root 1, and that's really just negative 1/2. So we also have f prime of 0. What's the linearization? The linearization L of x, if we combine all this stuff together, it's negative 1/2 times x minus 0 plus 1. For this one here, I think it's just best to not put the minus 0. We'd have negative 1/2 x and then plus 1. So this simplifies nicely to this equation here. Okay, now that we have this linearization, I think we can use it to approximate the square root of 0.99. This is different because the question is, to use this function to get this approximation, what do you put in place of x? So let's do that down here. I want to approximate this. I don't want to use this formula to do it directly. I want to use this one because it's a simpler formula. Well, the function we're using to get this first is this thing here. It's the square root of 1 minus x. So I'm going to put down, well, this should be equal to the square root of 1 minus something. What would you subtract from 1 to get 0.99? That number is 0.01. It's important to write this way as the function f of x, because this thing is now approximately equal to this, with 0.01 in place of x. So this is approximately our linearization at 0.01. What is our linearization at 0.01? It's negative 1/2 times 0.01 plus 1. All right, let's simplify this. I love 0.01. That's equal to, well, it's really negative 0.5 times 0.01 plus 1. Okay, that's negative 0.005 plus 1, which is 0.995. If we put this all together, the square root of 0.99 is roughly, approximately equal to 0.995. So this is the final answer. The other topic in this section is differentials, which are denoted by dx and dy. And these come from dy dx, the derivative of your function, is equal to f prime of x. So here this dy means, how are the y values of your derivative changing? And here dx means, how are the x values of the derivative changing? Below is a graph of f of x is equal to the square root of x minus 1. How much do the y values increase from x equals 2 to x equals 5? This is not a question about the derivative of this graph. This is a question of, as you go from x equals 2 to x is equal to 5, how much do your y values increase by? And here we can answer that by using the formula for slope, where here delta y is a change in y values, and delta x is a change in x values. So before answering this question, if we see a dy and a dx, this d means we're talking about how the x and y values of the derivative are changing. When we see this notation and this notation with a delta, we're talking about how the x and y values change on the actual function itself. So if we go from x is equal to 2 to x equals 5, we can easily answer what delta x is equal to. It's 5 minus 2, which is 3. So the change in x is 3. What is the change in y values? We're starting at y is equal to 1, and we end up at y is equal to 2. So this is 2 minus 1, or 1. So what is delta y over delta x? The y values went up by 1. The x values went over by 3. Essentially what this says is the slope between these 2 points is a third. So again, the delta x is the change in x values. Delta y is the change in y values on the actual function itself. Now let's ask the question about how are the x and y values on the derivative changing? That is, I want to compute dy if dx is equal to 3. So that is, if we go a distance of 3 for x, how much does the derivative at this point change by? Well, the derivative isn't the actual function itself, but you can visualize it by drawing a slope of a tangent line, which I'll do next. So here, if you actually draw the tangent line, you get something like this. And we're saying that if you start here and you go over 3, that's dx, you go over 3, how much does dy change by? So in this case, if this is dx, this distance is dy. Let's not compute it just yet. Let's just take a moment to understand the difference between the part that we did here and the part that we're trying to answer here. This part, the delta x and delta y, was talking about the original equation itself. Dx and dy is talking about the derivative. the way the derivative changes is based on the slope of this tangent line. dy is going to be different than delta y. So how do we go about figuring this out? Like, what is this equal to? Here are the mechanics to solving this problem. The function f of x is y is equal to x minus 1 to the 1/2 power. So that's this function here. And I'm first going to find dy dx. So dy dx is equal to, you bring down the 1/2, you copy down the x minus 1, and you subtract 1 from the exponent. So if this is our original equation and you take its derivative, it's equal to this. This is f prime of x. What we will do is treat this as a fraction and multiply dx to the other side. So we have that dy is equal to 1/2 x minus 1 to the negative 1/2 times dx. So we can treat this thing over here as a fraction by multiplying this to the other side. We now have an equation that will tell us if you know dx and you know the x value that we're referring to, which here is at 2, we can figure out dy. I'll put 2 in place of x. I'll put 3 in place of dx, and what will be left over is dy. dy is equal to 1/2 times 2 minus 1 to the negative 1/2 times 3. And if we simplify this, or let's see, 2 minus 1 is 1 to the negative 1/2 power is also 1. This is 1/2 times 3. And you could write that as either 3/2 or 1.5. So this here is the value of dy. And what does that mean? The derivative, as we went over 3, it actually goes up by 1.5. The actual function, when you go over by 3, only goes up by 1. So when talking about differentials, we're talking about how the derivative changes and not the actual equation itself. And we can use this formula here to compute it. In our last example, we're going to find the differential dy for these two equations. And just to state how to compute this, if you have that dy dx is equal to the derivative of a function, we can treat dy dx as a fraction and say that dy is equal to f prime of x times dx. So to compute dy, all I'm going to do is take the derivative of this side of the equation and then multiply it by dx at the very end, and that's it. So what is dy? It is the derivative of this side with respect to x times dx. What is the derivative of this side? I'll have to use the product rule. We get the derivative of the first times the second plus the first times the derivative of the second, which is cosine of 4x times 4. Before we would write this side as dy dx. However, we're going to take the entire right side and multiply it by dx. The differential is just the dy, and it's equal to this entire thing here. What about here? What is dy in this part B? It is the derivative of this side of the equation times dt. So the derivative of the natural log is going to be 1 over 4 plus t squared. By the chain rule, you have to multiply by 2t. And at the very end, I'll put dt. Before, we would have put dy dt on this side of the equation, but we'll treat it as a fraction and multiply the dt to the other side. So unsimplified, here are the differentials dy for parts A and B. Note that it's the same as taking derivatives like we've done before with one extra step. We take this denominator and multiply it to the other side of the equation.